Hello, my name is Paul de la Aguila, and I'm a research staff scientist at the CIBM Center for Biomedical Imaging and a postdoctoral researcher at the BFL's Biomedical Imaging Group. So I'm here today to present to you the work Stability of Image Reconstruction Algorithms, which we published recently in the IEEE Transactions on Computational Imaging. In that work, we focused on image reconstruction algorithms, which are the algorithms that take you from the measurement into the actual images we want to obtain in applications in modalities such as MRI, CT, PET, etc. So what we focused on specifically is on the fact that recent works have suggested or shown that at least practically, many image reconstruction algorithms that are state-of-the-art are not stable with respect to the small changes in the measurement. So by disturbing the measurement slowly, we can really break the reconstruction, which is concerning because image reconstruction algorithms are utilized in modalities where the end application can be diagnosis of certain diseases, or it can be biomedical research. So an unreliable image reconstruction algorithm would make the whole pipeline unreliable. So what we propose is to go back to fundamentals and try to find which methods in image reconstruction provide this kind of guarantees, like where you can bound the norm between the images reconstructed under two different measurements by a factor times the norm of the difference between the two measurement vectors. And here we have a constant k, and this constant k will be important because some methods fulfill this property, but for a constant k, we don't know how to compute, and some methods will not even fulfill it. So the first thing we do is we review the history of image reconstruction under a reference variation problem, since most of the history of image reconstruction is based on variational methods or direct methods, which are even easier and can be interpreted also as a subset of variational methods. So first off, we analyze what happens with Tikhonov regularization, where it's well known, but it's still interesting to see that the result is that we get Lipschitz stability with respect to the measurement disturbance. So we have a kind of a strong stability result with a constant that we can compute straight away. The details I will explain in the poster presentation at the conference. For sparsity-based regularization, we have a similar result. It's positive, but provided that we are in the case in which sparsity-based regularization leads to a single solution. When the conditions of the problem are not such that there's a single solution, even discussing stability doesn't make sense, because different algorithms or the same algorithm with different initializations would yield different reconstructions, and therefore the meaning of stability loses a bit, is completely lost. Then here it's interesting even to see that in sparsity-based regularization, even when there is a guarantee of Lipschitz stability, the constant k is hard to compute or to bound. It's a bit hard to treat. Then what our new results are actually about when one uses LP regularization, which is basically a bridge between L2 and L1 regularization for any p between 1 and infinity. And under that setup, we can apply recent results to characterize better the set of solutions of those problems. And from those results, we obtain two different bounds, one for p between 1 and 2, and one for p between 2 and infinity, that characterize the stability of these methods and give the tighter constants for the stability, their stability, and they're all interpretable constants. Throughout the presentation, we will have an interesting discussion on the role of the operator norm on how stable the reconstruction process is in an imaging application. So if you want to know all the details and you want to know the math that we use to prove those two bounds, please come to the poster in Greece, and I hope to see you there. Thank you.